Hello, I'm Hong Kim. As in the last presentation, I selected a paper related to MIS. Today's paper is continuous multiple importance sampling. Before the presentation, I will first explain the flow. First, I will briefly explain multiple importance sampling once again. Next, let's look at what continuous multiple importance sampling is. Finally, I will present two applications with the introduction of related previous works. Then let's move on to MIS. For some integration problems in rendering, finding the exact solution can be exceptionally difficult. So we can approximate the solution instead using Monte Carlo integration. Ideally, to reduce variance of estimator, we want a distribution of samples that is proportional to the function we are integrating, such that higher regions are sampled more often and lower regions are sampled less often. This is called importance sampling, but it can be difficult to design one technique that importance samples the entire integrand well. Instead, we can try to combine multiple techniques. For example, one that's good at sampling the left side, one that's good at the middle, and one that's good at the right side. This is called multiple importance sampling. For formulation of MIS, we divide the effects according to a certain weighting technique, and then we can break down the integral into sampling techniques numbers T weighted integrals. Visualizing this as SIGGRAPH is as follows. We then estimate its weighted integral with a different technique. Given this decomposition and having chosen how to estimate its weighted integral, there are two options for estimating their sum: one sample MIS and multi-sample MIS. One sample MIS estimates the integral by randomly selecting a technique and a sample from its weighted integral. Each technique is assigned a probability of selection, and from the set of techniques we stochastically select one. From that technique we draw a sample and use it to make an estimate of the integral. In contrast, multi-sample MIS opts to estimate its weighted integral and sum them. From each technique we choose one or more samples. So these are one sample and multi-sample MIS estimator. We would then ideally want to find a weighting function that results in efficient estimators. As I introduced in the last presentation, Beach and Galbas proposed the probably good balance heuristic that a weight of each technique is proportional to their PDF. In addition, in the last presentation, an optimal MIS using weighting function that minimizes the variance of the estimator was also introduced. Now let's move on to the main topic, continuous MIS. Continuous MIS is a generalization of multiple importance sampling to continuums of sampling techniques. From now on, we will call the previous MIS, which had a finite number of sampling techniques, the discrete MIS or DMIS. In DMIS, we had assigned a discrete sampling technique to each weighted integral. But now that we have a continuum of integrand techniques, here HT is technique identifier. Like DMIS, CMIS also has a corresponding one sample estimator. In DMIS, we select a technique with some probability, and from it a sample was some density. In CMIS, as we know, have two continuous random variable x and t. We can sample them according to their joint probability density, giving us an ordinary Monte Carlo estimator for the double integral. T1 sample TMIS and CMIS estimators are analogous. We normally sample a technique first, which leads to the following factorization of the joint probability density, where we see that the utilized probability of technique selection in TMIS becomes the probability density in CMIS. And what was the probability density of a sample for a specific technique in TMIS is now the conditional probability density in CMIS. CMIS has a balanced heuristic that is probably optimal. Here, what was the sum over the techniques becomes an integral. Now, it seems that we just need to apply the CMIS directly to the practice. But unfortunately, in many applications, this integral in the CMIS weighting function denominator is not available in closed form. So this paper found a way to stochastically approximate it and still achieve unbiased estimation. This new type of MIS is called stochastic MIS. Instead of directly solving for the integral, they sample several techniques and sample pairs from the joint distribution. And we can use the techniques of each pair to make Monte Carlo estimates of their weights. As each technique is drawn proportional to its marginer, the estimator in the denominators simplifies to just an average of the conditional sample densities, which in most applications is already available. If we use this approximated weights in a T-sample CMIS estimator, we have the following. This appears to be a multi-sample TMIS estimator with a balanced heuristic. But here, the key difference is that the techniques are chosen stochastically. Then, where can CMIS be used? From now on, I will talk about the two applications in the paper. First applications of the CMIS framework is isolating Monte Carlo path tracing via path reuse. In path tracing, the bore information can be obtained, so accurate rendering result can be obtained. However, if we sample a lot of paths, the cost becomes too large. In previous work, path filtering, a method of using an existing path is proposed to generate paths at a low cost. Path filtering generates a filtering corner where the corner is a series of heuristics chosen to reduce bias. When any next generated path reaches the filtering corner, the remaining path is set of the existing path that generated the filtering corner. As the vertices are close, we can forego expensive re-evaluation at the cost of introducing a controllable amount of bias. There are some problems. First, this is bias method. Second, this works well on diffuse materials, but it has some difficulty with closed surfaces in detailed geometry. To solve these problems, this paper split a path into preface and a surface. Preface is before reaching a certain point, and surface is after reaching. The preface path conditions the sampling of a surface path, so we can treat each prefix as a sampling technique. As any path can be a prefix path, we have a continuum of techniques and can apply it as MIS theory. In fact, this method is not just limited to path filtering, so this method can achieve an unbiased general path reuse estimator where each connection is weighted with SIMIS. Paper have a highly closely spaced scene rendered with 3 different methods given the same time budget. Here on the left, there is a path tracing which as a baseline. In the middle, there is color path filtering, where bias due to filtering is visibly noticeable. And on the right, there is a SMIS-based path filtering which shows not only reduced bias compared to Keter technique, but it also shows reduced noise compared to path tracing. Second application is in spectral rendering. In spectral rendering, we additionally consider how much light is transported for each wavelength. Spectral rendering overcomes the limitation of tri-stimulus RGB rendering by extending the path integral over the visible rays wavelength domain. In spectral rendering, first wavelength is sampled, and then n wavelengths based on that wavelength, and then a path based on those n wavelengths. The distribution of wavelengths often takes into account camera responsivity and the emission profile of light sources. Wilkie proposed to select a first wavelength according to this distribution and then select a set of evenly spaced wavelengths around it. This corresponds to having n-sample technique for each wavelength, which are combined via balance heuristic TMIS. However, its uniform wavelength spacing is suboptimal for spectral power distribution that concentrate energy at a few peaks, such as fluorescent light. This problem is solved very simply by applying the SMIS. By considering wavelengths as a continuous technique variable, more accurate results can be obtained by considering more diverse wavelengths. And since wavelength is sampled stochastically, thus impedance sampling is applied, accurate rendering results can be obtained for Fluence light source. Here there is a simple scene with a gold dragon lit by a fluence light and comparison the estimation error of three different methods. Hero MIS, which was introduced as previous work, stochastic MIS using independently sampled wavelengths, and a brute force method. All methods use the same number of paths and 4 wavelengths per path with the exception of the brute force method, which uses 512 wavelengths per path to provide a good ground truth on color noise. As the fluorescent light has a peaky power distribution, the scene is challenging for halo MIS, and there's quite a bit of color noise present. In contrast, as MIS estimators shows reduced color noise, on the right being almost visually indistinguishable from the brute force method. So far, we have looked at the CMIS and SMIS introduced in the paper, starting with the concept of MIS, and have looked at the 2 applications. Thank you for listening to my presentation.